except we're going to move on to another type of test that we can do with categorical data that's more dynamic. All right, so right now, if you wanted to do a hypothesis test with categorical data, you're limited to asking more or less like yes or no questions, right? Are you in favor of this policy, yes or no? And you can do a hypothesis test on what % of people answer yes, right? But if you wanted to study something that was more complicated than yes or no, like what day of the week do you go and visit this store, and there's multiple options, you could do this with a proportions test, a z-test, but you would really have to force it. It's really not built to evaluate this type of data. So we would want to have a test that's more built to deal with complex categorical data. And that's what we're going to learn how to do in this unit. We're going to learn 3 types of tests. These are called chi-square tests. We're going to learn 3 types. We're going to do one of the 3 today, and we'll do the other 2 next class. So the first type of chi-square test that we're going to look at is something called a chi-squared goodness of fit. All right, chi-squared goodness of fit. This looks like an X. It's the Greek letter chi. It's spelled C-H-I, so it's spelled like chi. All right, but it's pronounced chi. Chi-squared goodness of fit. All right, this is going to be the first type of chi-squared test that we're going to learn. And each one of these tests are going to be used in different scenarios depending on what our data and what our groups look like. So this type of test we're going to be using when we're studying one group, so one population. All right, so we're not comparing 2 groups, we're only looking at one group. We are only looking at one variable, so we're only asking one question. In this case, it's what day of the week do you visit this store? And that variable has multiple possible responses, so 2 or more. You could do it with just 2 responses. It would be kind of silly. You could just do a z-test if you only had 2 response types. Here we've got 6 potential responses or ways that an individual could respond. All right, so if we're looking at this, here's the scenario. It says that we've got this company, and they believe that the distribution of customer arrivals are as follows. So they think that 10% of people that visit the store come in on Monday, 10% on Tuesday, 15% on Wednesday and Thursday, and then it picks up at the end of the week with 20% on Friday and then 30% on Saturday. So that's what they think is happening. And they want to investigate whether this model, whether this expectation is correct. So they take a sample of customers and when they visit the store, and they want us to use this sample to evaluate whether this model is a good fit or whether we have good evidence to say that this model is wrong. All right, so that's the task that they're asking us to do. So what we're going to do is we're going to do a hypothesis test. And the steps for this are going to be the same. All right, so the logic, the whole procedure is more or less the same. It's just the mechanics of each step are going to be different, but the logic is going to be the same. We're going to write our hypotheses. We're going to check conditions. We're going to calculate a test statistic. We're going to mark it on a sketch in shade to find p-value, and then we're going to use that p-value to either reject or fail to reject the null. So our hypotheses. All right, now you'll notice that I'm giving myself a little bit more space. All right, and this is because in this unit, because we're studying more dynamic data, we don't really have like one parameter that we're testing, right? It's not like p equals and then some number, because we've got a bunch of different responses. All right, so this particular one, we could write symbolically, or at least we could write the null symbolically. it's a little bit easier, and typically people will just write all of the hypotheses for chi-squared in words, so that's going to be what we do. All right, so the null for this test is going to be that the true distribution, and this is always going to be the null for goodness of fit, the true distribution of whatever you're studying, in this case it's of customer visits, is the same as, and then wherever your expectation is. In this case, is the same as the store's model. All right, so this is going to be the null for all of your goodness of fit tests. And the only thing that would change is this underlined part. All right, so if you're studying something else, whatever you're studying would go in this spot. And whatever your expectation is would go in this spot. We will do more examples of this on Friday, where you'll get to see another one where we have a model, and then another one where they don't give us a model, and what do we do in that case if they don't spell out what we're supposed to see? It's actually pretty easy. All right, so that's the null. The alternate is just going to be the opposite of that the true distribution is not the same or is different from the model. When we say is different from the model, though, we don't mean that like this model is all wrong necessarily. When we say that it's different from the model, we're saying, hey, at least one of these categories, at least one of those percentages is wrong. So at least one area of this model is incorrect. So we'll just write that. So the true distribution of, again, customer visits is different from the store's model for at least one day of the week. And again, the only thing that are going to change is the context, where you got your expectation from. And we're saying that it's different from that expectation for at least one of the, whatever your categories are. So in this case, our categories are days of the week. And this is always the order, so you never have to worry about, hey, should these be switched? The null is always that the true distribution is the same as whatever our model is, or that our model is a good fit. That's why it's called a goodness of fit test. We're looking to see, is this model a good fit for our data? And our alternate is always that this model is not a good fit. Because there's no parameters, we don't have to define our parameters. That's the first step done. Questions on the hypotheses. Okay. And we'll move on to the next part, which is checking conditions. Now, when we learned hypothesis testing the first time, there was 3 conditions. In the last unit, when we were comparing 2 populations, we added a 4th condition. We're only doing 1 population here. So independent groups is not a check. All right, we only have 1 group that we're studying. So we're back down to the original 3. All right, the difference is the first check. All right, this first check, we're no longer doing a normality check. This is a chi-square test. And so when we get to the math step and we draw our sketch, it's not going to be of a normal distribution. It's going to be of this new shape that we haven't used yet called a chi-squared distribution. All right, so it's gonna look visibly different. But we're not doing a normality check here. We have a check that makes sure that that shape is true. So we are doing a check here, but it's not called a normality check. And if you write normality and then do a check here, they will not count that. All right, so this is not a normality check. But the check that we need to do to make sure that our sampling distribution follows the chi-squared shape is we need all of our, what are called our expected counts, need to be at least 5. Now you don't know what our expected counts are yet. Don't worry about it. We'll come back to that in 1 second. But we need all of our expected counts to be at least 5. The other two checks would be the same. It would be a random sample or a random element. In this case, it's a random sample, and that's stated. And then the optional check, which is independent samples, aka the 10% rule. All right, so the other two checks are the same. And again, this one I don't make you check. All right, so now we need to address this guy. Are all of our expected counts more than 5? So to check that, first we're going to need to come up with our expected counts. To come up with expected counts, first we need to know what our observed counts are. All right, our observed counts is what did we see when we gathered our data. So your observed counts will always be provided to you in the problem. This is the results of our sample. Our observed counts are these numbers down here. This is how many people came in on Monday, Tuesday, and Wednesday. That's what we observed. You don't actually have to write them as a column, but I'm doing this because I think it's going to help you guys learn better. So these are my expected counts for Monday through Saturday. If you add all these things up, that's 215 people. That would be my sample size. All right, those are my observed counts. Now we have to calculate our expected counts in this test. But I'll tell you, I haven't taught you this yet, but I think that you guys could probably figure it out. All right, how we come up with this. All right, here's the logic. All right, we just watched 215 people come into the store, right? And this model is what we expected to see. This is what the store is telling us. So if the store is telling us that we expect 10% of our customers to come in on Monday, and I watched 215 people come in the store, how many of them should have come in on Monday? Yeah. And actually, that's exactly right. So, and you said it too. 10% of 215. So you're just going to do 0.1 times 215, and you're going to write it as a decimal. Like you just said, Maddie, it's 21 and a half would be my expected count. Now, I understand that we can't have this many. We're just saying on average, if we were to watch this store over and over and over again on Mondays, if this was true, on average we should be averaging about 21 and a half people coming in on Monday. Yes?
Are we going to have to show observed and expected counts like for breakdown?
That's a good question. So observed counts, those will be given to you. Your expected counts you are going to have to show. And in terms of the work, I think you should at least show the work for one of them. So 10% times 215. And then the rest of these. And then if you do this right, and you add up all of these expected counts, it should add up to be 215 again. All right, so this is just 10% times 215, 0.15 times 215, 0.2 times 215, 0.3 times 215. So you're just finding those percents of 215. All right, now I want to make something explicit because, not that this is hard, but this is probably the place where kids mess up the most on this test is coming up with these expected counts. Let me tell you two things that kids do wrong so that you avoid it. All right, the first thing that kids do wrong doesn't really make any sense. All right, they'll do like 10% times this number and get like 3. Then all of these expected counts are going to be very small. If you add these all up, it's not going to equal 215. All right, it should be a red flag that none of these are even close to these. All right, that would be a red flag. All right, now the second thing that kids do wrong, and I need everybody to pay attention to this because this actually makes sense why kids would do this, but it's wrong. All right, is we want everything in terms of observed counts. What some kids will do is they'll say, oh, well, I have these percents. Why don't I convert all of these into percents and then compare my expected percents and my observed percents? So they'll say, oh, what percent of 31 of 215 is 31, right? And I'll have all these as percents. That makes sense, what you're doing. The problem is it's going to give you the wrong answer because mathematically, your test is thinking that you only observed 100 things when you really observed 215 things. So you need to turn it in terms of counts, not in terms of percents. Does that make sense what I'm saying? Okay. All right. So these are my expected counts. Now that I have those, I can address this check. Are all of them more than 5? They are. How I show this is I'll just say whatever my lowest one is. My lowest one is 21.5, and that's more than 5. Okay. All right, third step is the math step. So it's going to work very similar to our other hypothesis tests. We're going to calculate a test statistic. We're going to mark that on a sketch. We'll shade and we'll find the area for our p-value. Now, we're not going to use this equation that we used previously. We aren't testing a single parameter anymore, which is why we can't use this. What we are going to use is still on this same page here, is this equation is what we're going to use for all of our chi-squared test statistics, so for all of our chi-squared tests. And this is a summation, so it's a big addition problem. Essentially what you're going to do is for each category, you're going to find the difference between your observed minus the expected squared over the expected. So you're going to do that for Monday, plus, and then you would do it for Tuesday, plus. Now, you don't need to show all of that, but that's what you would be doing by hand if you had to do this by hand. All right, here's what I want you to do for me. All right, chi-squared, I'm just going to write the equation. Observed minus expected squared over expected. What I want you to do is just give me the first term and the last term, and then we'll just do an ellipses in the middle with like a plus, a dot, 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 and we'll just skip over the middle. So just give me the first and the last term. So give me Monday and give me Saturday. So for Monday, my observed is 31 minus 21.5 squared over 21.5. So there's the term for Monday. Plus, now if I was writing this all out, I would do Tuesday, Wednesday, Thursday, Friday, but I'm telling you I don't need you to do that, so just go plus, dot, 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 and then just give me the last term, so give me Saturday. So Saturday is observed was 60 minus 64.5 squared over 64.5. All right, and this work is going to give me my test statistic. When I have my test statistic, I'm going to mark it on a sketch, and then I'll shade, and I'll find that shaded area. Now, doing all of this is a hassle, so we're going to let the calculator do it. So, first part of this is your calculator needs your lists. It needs your observed counts, and it needs your expected counts. So you're going to put both of these in, observed in one list and expected in the other. So I put my observed in L1 and my expected in L2. So start off, do that for me real quick. Again, that's stat edit. That's how you get to this. And the default is observed in L1, expected in L2. That would be the easiest way to do it. You could switch these, but if you switched them, then you're going to have to remember in a minute when we tell the calculator to do the test where to look for your observed and your expected. Your calculator, as a default, expects the observed to be in L1 and the expected to be in L2. All right, so once you have those lists entered in, we can run the test by going to stat tests, so the same place that we go to do all of our tests. Now you've done most of these tests now. Now if you could scroll down to get down to the chi-squared ones. It's actually easier to scroll up because the list is so long. So now we're down to the bottom of these things. So there's two types of chi-squared tests that your calculator is going to offer you. If you have a TI-83, I don't know if anybody has an 83 in here. TI-83s don't do goodness of fit. This is like one of the few things in here that the 83 doesn't do that you need. So just on test day, make sure you let me know, and I'll let you borrow an 84. At any rate, we're going to pick, out of these, we're going to pick D. This is the GOF, stands for goodness of fit. So we're going to pick the chi-squared goodness of fit test, hit enter on D. All right, now my observed are in L1, and my expected are in L2. All right, and then it's going to ask me for degrees of freedom. And guys, I don't know why it asks you for this, because it has everything that it needs to calculate degrees of freedom, so I'm not sure why it makes me say what it is. I also don't know why everybody has 5 in there right now, right? I don't know why it says 5 as the default. That does happen to be the degrees of freedom in this problem, but that is a coincidence, all right? I don't know how it happens that random number is the default in your calculator and also happens to be the degrees of freedom in this problem. All right, how you calculate degrees of freedom for goodness of fit tests is the number of categories that you have to your question minus 1. And I know categories doesn't begin with K, but in the next chi-squared test, we're going to be using these tables that have rows and columns, and they use C for columns. So they give categories the letter K. I don't know. But it's the number of categories your question has minus 1. So our question allows for 6 possible answers. So it's going to be 6 minus 1, which is 5. So my degrees of freedom in this problem is 5. I just don't know why that's the default. At any rate, when we hit calculate, it's going to give us a bunch of stuff. All right, this top line, that 8.54, that is the result of doing all of this number crunching. That is my test statistic. And we call that value a chi-squared statistic. So just like we would, if this was a z-test, we would call this a z-value. Or if this was a t-test, we would call this a t-value. This is our chi-squared statistic, or chi-squared value. All right, this screen also gives me p-value, which I need. So I might as well write that down. But let me show you guys how to find this p-value so that we know how to do it. All right, the logic is the same as our previous units. We're going to take our test statistic and we're going to mark it on our sketch, except in this problem, our sketch is no longer of a normal distribution. It's of a new picture that you guys haven't drawn before. It's of a chi-square distribution. All right, a chi-square distribution is just like a skew right. It's just got a tail on the right. So chi-square distribution always starts at 0 on the left. And then most of the time it looks like this. So if you just want to draw it like this all the time, that's fine. It is always going to start at 0 on the left. It's always going to tail off on the right. That's always true about it. There's not as many distinguishing characteristics or like landmarks on this picture as we have for the normal distribution. So drawing this to scale is actually kind of hard. I will tell you one thing about it. Now you guys don't need to know this, so if you're just like, I don't like that, it's fine. You don't need to know it. But if you want to know it, this peak is going to occur at degrees of freedom -2. You don't need to know that. There's not going to be a question on a test about that at all. But if you're just curious, this peak is going to occur at degrees of freedom -2. So in this case, this peak is at 3. Why I like that personally is it helps me eyeball. Okay, so if 0 to 3 is there, then that's 6. So 8's maybe like over here-ish. It like helps me eyeball where to put the test statistic a little bit. It doesn't matter. This sketch doesn't need to be to scale. So if you want, you could always just draw this. Don't even have a mark here, and just put your test statistic somewhere over here on the right. All right, and that's fine. The last thing I'll say about this, and again, this is another thing that you don't need to know, is in the event you can have degrees of freedom that are really low. Like you can have problems where the degrees of freedom is 2 or 1. If the degrees of freedom was 2 or 1, then my peak would be at 0 or -1. In those cases, your chi-square distribution just looks kind of like a ski slope like this. All right, when your degrees of freedom is 0 or 1, it looks kind of like this. You don't need to know that, but if you're ever like doing a problem, you might see that they draw the sketch like this, and you'll be like, "Whoa, Mr. Grossman, that's not what he draws when he does it." That's a special case when you've got really low degrees of freedom. Again, you don't need to know that. All right, what you do need to know is draw a sketch, tails off on the right, take your test statistic, mark it on there, and then you're always shading to the right. All right, so you don't have to worry about is it one-tailed or two-tailed, or am I shading to the right or to the left? You're always marking on this right-hand side, and you're always shading to the right. And then we're going to find that shaded area, and that shaded area is going to give us this p-value. Now, to find this shaded area, we're not going to use norm CDF because this is not a normal distribution, and we're not going to use TCDF because this isn't a t-distribution either. This is a chi-square distribution, so to find the shaded area, we're going to use a function that you guys haven't used yet, called chi-squared CDF. Chi-squared CDF is under dister, and I'll just tell you, chi-squared CDF, you get in there, you could probably figure out how to do it. It's the same as all of our other ones. It's lower bound, upper bound, degrees of freedom. So here, my lower bound is 8.54. My upper bound is positive infinity. And my degrees of freedom is 5. And that work is how your calculator came up with the p-value of 0.129. All right, at this point, it's the same. All right, now we're going to use our p-value, compare it to our significance level. All right, how good is our evidence? Is it low enough? So here, my p-value is 0.1, is almost 13%. My significance level is 5%, so it's not low enough. So because our p-value, 0.129, is bigger than my significance level of 0.05, fail to reject null hypothesis. Olivia, we'll be done in a minute. All right, we fail to reject the null. There's not enough evidence of whatever our HA is. There is not enough evidence to say the true distribution of customer visits is different stores model. Alright, so what do we think? Any part of that you would like for me to talk about again? Alright, I got one more small thing to go over. Alright, and that is when you ran stat tests and did this test. Alright, you got your test statistic, your p-value. It gives you degrees of freedom. I just told you degrees of freedom, calculator. All right, so while you're telling me this back like you're helping me, I just had to tell you. All right, and then it gives me this other line called conturb. All right, now what this stands for is contributes or contributing. All right, it's telling me for each one of the terms, each one of my categories, when I went through and I did this big addition problem, how much did each one of those days of the week contribute to my test statistic of 8.54? So it's giving you like how much did this Monday term, how much was that Monday term? Monday was 4.2-ish. All right, Tuesday If I scroll over, there's Wednesday, there's Thursday. And if you added up all these numbers that are in this list, it should add up to be 8.54. It's just giving you each of the 6 days of the week that we evaluated. All right, now, why is it giving me this? Why does it think that this might be useful? All right, so this is information that could be useful if you were asked to do additional analysis. So if, for example, they gave you this question and then they gave you a part B, and the part B was something like, hey, the store owner is considering adjusting the employees' schedules so that the store has either more employees on busier days and less employees on less busy days. If you were advising the store manager, which days of the week would you recommend that they adjust and why? All right, so right now I actually don't think that you would need that list at all. But if I just asked you straight up, hey, if they were adjusting the schedule so that they brought in more employees on busier days and less employees on less busy days, which days of the week do you think that they should be adjusting based on what they saw and what we expected to see? Does anybody have like a thought on which days you would want to adjust? Which one? All right, so fewer on Tuesday and Thursday. Certainly on Thursday. Why would you say fewer on? Oh, and then fewer on Tuesday. Okay, and then more on which days? Certainly on Monday. Certainly on Wednesday. Now, which of them are the most dramatic? I think most people would say that Monday, you definitely should be bringing in more employees. We saw 31 people, and we expected to see 21, so we saw quite a bit more. And then on Thursday, bringing in fewer people. We expected 23. We only saw 32, so that was like about 10 less. If that was your answer, if your answer was, I would recommend for the store owner to bring in more people on Monday because we saw 10 people more than we expected, and I would recommend they bring in fewer people on Thursday because we saw roughly 10 fewer people than we expected. If that was your answer, I think that would get you full credit and you wouldn't need to say anything else. All right? What you could also point to is you could point to these values in this contributing list. All right? One of the things, the limitations of saying, oh, there was 10 more people on Monday than I expected, is 10 people is relative. All right, what I mean by 10 is relative is like, if I expected 1,000 people to come in on Monday and we got 10 more than expected, that's not really that big of a deal because I was expecting 1,000 people. All right, but when I'm only expecting 20 people and I get 10 more than I expected, that's like 50% over what I expected to see. Does that make sense? So how far off you are really needs to be adjusted for relative to what your expectation was. That's what this contributing list is doing. It's just telling you, it's a metric that boils down how off was each day and then relative to the expectation. So the bigger this number is, the jankier that day of the week is. So Monday is contributing like 4.2. That's almost half of my chi-squared statistic. So Monday is a pretty janky day. Tuesday, 0.6, so not that much. So Tuesday's not that bad. Wednesday, 0.4. Again, Wednesday's not that bad. Thursday, 2.6. So more dramatic than the other days, but not as dramatic as Monday. And then if we get to Friday and Saturday, you'll see that those are in the 0.3-ish range. So both of those days, not too dramatic. So you could use this and those values as a resource or something that you could point to and say, hey, I would recommend that you change Monday. Monday contributed the most to my chi-squared test statistic. All right, so it's the day where the difference was the most dramatic relative to the expectation. And I would recommend that you bring in more people on Monday because we observed more people than we expected. So that would be a perfect answer. Questions?
on that. Okay, we're done.